her name. So I hope that I said her name very well. Okay. So her talk will be on a data-driven approach to managing a pandemic, learning from the field. So let me introduce to you Srujana Merugu. She is a principal scientist at Amazon. Srujana has nearly 2 decades of experience solving large-scale data science problems in the internet, enterprise, and e-commerce domain as part of the machine learning group at corporate research labs. She is active in research through publication in top machine learning venues such as KDD, ICML, SDM, CIKM, and ICDM with multiple best paper awards. This is amazing. She has also 5 years of experience in consulting practice on data science strategy, setting up data science teams and processes. She's focused engagement with multiple startup and non-profit organization in education, healthcare, and fintech domain. Some of her machine learning application domain are in information retrieval recommendation system. Srujana obtained her master and PhD in computer engineering from the University of Texas, and she obtained also her bachelor from the well-known IIT from India. So welcome, Srujana, and I hope that I pronounced your name correctly. Welcome.
Hey, thanks so much, Halima. Thanks for the kind introduction, and thanks to G, Dr. Shizong, and others for inviting me over. It's like really nice to be here and this Women in Data Science event. And in fact, like I was pleasantly surprised to see a fellow Longhorn as well. So let me, start my talk. I could probably start with a little story, but let me just make sure I have my screen sharing in place. Give me a moment.
Take your time. We are here waiting for
Could you just walk me through it? Share, what do I share? Is it an event window or screen?
When you click on the share button, you should click on the PowerPoint presentation. Yes, we can see it now.
You can see it. All right. Awesome. So just wanted to make sure this is all perfect. All right. Sounds good. So I just wanted to, start with a little story, in fact. So just a few days back, I realized that the theme for today's event is actually data science and education. And my talk is on COVID-19 response, which might not directly relate to applications of data science in the education domain. But in any case, I felt it would be educational in terms of how one can take this precious body of knowledge and solve some of the world's pressing problems, whatever be the application domain. Now, before getting to the talk, I also want to share a little story which kind of drives my motivation to engage with more people in the community. So last year around August, I was having a conversation with some friends who were working with the COVID war room at Mumbai, which is the largest city in India. And for 4 months, every day at midnight, this team used to download the COVID test results from our central portal. They would fix all the duplicate records and map people to local regions within their city and send out all of the patient lists by 7 in the morning to the local teams. And this is the much lauded decentralized setup that help folks manage the pandemic in Mumbai. The unfortunate part there was that this brilliant team actually did not include a single formally trained data science person. And they were just hustling and getting the job done. So when a couple of us data scientists joined them, it meant a big deal to them. And all those friends had this overwhelming conviction that last year's crisis was just a dry run and that we desperately need an all hands on the deck approach. And this is true across the world, not just in our city, in our country, but there are just so many things that need fixing in our world. And each of us, including little kids, right, have a role to prepare for what is next. And beyond this pandemic itself, we have the defining challenges of our generation. This could be climate change, the consequences of automation, and societal divides of all sorts staring at us. So I feel there's both an obligation and an opportunity to bridge the worlds of need and the worlds of surplus when it comes to science and technology, and actually do that at scale. And as data scientists, we are all a relatively privileged lot who have the skills to make a difference. And that's one of the reasons I wanted to, be here to connect with more folks and also share my experience and learn from others. Now, coming to the talk itself, what I have for you today is a four-part story. So first I'll share a little bit on my COVID response journey as part of an amazing consortium team. This is not work I did at Amazon, but this was prior to my time at Amazon as a volunteer working with a lot of other folks. And then a quick overview of the pandemic control loop and the data science problems that emerge. And then we'll take a slightly deeper look at epidemiological modeling and some of the reflections from this experience. And I would request folks to, feel absolutely free to stop me and ask questions, or the only problem is the time constraint and I might not be able to see them on time. So, or we could get to it at the end of the talk. So please feel free. Now, let me start with an overview of the response effort itself. So this was the work of a large multi-organization team, and I will share the story from my perspective as a research lead. So last March, some of us data scientists were concerned about the pandemic, and we got together as a volunteer group. And though we were mostly researchers, we began with this firm conviction that our effort had to be focused on the human impact and not become a mere academic exercise. So while on one end we started fleshing out possible technical problems and solutions, we were also actively reaching out to the various government task forces, war rooms, and a lot of other organizations that were trying to pitch in just like us. And as we interacted with various stakeholders, what we realized was that our ecosystem was highly fragmented. There were multiple private and government organizations responsible for health surveillance, care delivery, planning, and policy making. Even the ownership of data, the modeling expertise, and the engineering skills were distributed across multiple entities. So we data scientists were sort of like the folks sitting in this yellow box and wondering where's the data going to come from and who exactly will use what we build and why would they use it and how would they use it. So to cut the long story short, we realized that there was not much scope to make a difference unless the gaps were somehow filled out. And to bring order to this modeling chaos, it was critical to get a better understanding of the end user requirements and also somehow create these data and model management layers. The green boxes that you see in the figure here, right? They had to be filled out somehow. And with these goals in mind, our volunteer group joined a data science consortium, which had brought together multiple organizations to partner with the government authorities in India. Now, this turned out to be quite an eventful journey. So the early days were full of adrenaline rush. I'm guessing you all remember how it was last year around Feb and March, right? So we had inflated expectations once we started working with the Smart Cities Mission, one of the leading government agencies. And then the reality of the missing data and the clunky process hit us. So we soon figured that building dashboards with predictions was only a part of the job. Ensuring that the insights were understood correctly with all the caveats and actually factored into the decision making was a whole new ballgame. And this forced us to rethink the scope, our approach, and adopt a more end-to-end view. And I would say that even now, even though we are like kind of past the pandemic situation, right, we're still on this slope of enlightenment, and the job is clearly far from complete. And I hope you notice this timelines across multiple years. And we really have a long way to go before these systems are resilient enough to comfortably deal with a new pandemic. Now, coming to the actual work, here's a quick look at some of the collaborations which was spread across different cities and provinces in India, and also some engagements with the central government. Now, let me come to more of the problem setting itself, right? So let's look at the problems that emerge in the management of a pandemic, and this would be true regardless of the geography. So essentially what we need is a control loop. So there are 3 steps here. The first one is observing the state of the pandemic, and this involves monitoring various aspects such as the mobility, the disease and the economic impact, the situation with testing, medical care, vaccination, and so on. And the second one is making key decisions on the levers that we control. And this includes the lockdown policy, testing, tracing, medical planning, and vaccination allocation. Making the right choices here can result in a huge difference. Now, implementing these choices and executing on the ground is a third equally important task. And together, these 3 steps complete the loop. And as intelligent agents, we humans execute this loop all the time. In the case of a pandemic, however, the entire social collective needs to act as a unified agent, and we need to build systems to close this control loop. And since the clock is ticking all the time, we also need to be fast and smart. And that is why a data-centric strategy is critical. So essentially what we need are data-driven systems and an organizational structure that can be roughly imagined as a response pyramid. So the bottommost layer here deals with driving execution, and this would comprise the teams on ground such as testing and tracing units. The next layer is all about collecting and managing data in an ecosystem of apps, databases, and pipelines to make sure it's usable for actual decision making. And the data science and analytics layer involves interactions between domain experts such as epidemiologists, economists, and data scientists. And at the very top of the pyramid are the folks who are responsible for making decisions. And typically that is the government officials. And as you can imagine, the data here flows upwards, getting progressively more insightful, while the decisions and guidelines flow downwards. And given all our time constraints, I will just talk briefly about the 2 middle layers. So in the data collection and management layer, there are 3 important issues to consider. The first and the foremost is the representation itself. And this is true of any problem, in fact. And in this context, right, the very definitions of essential concepts, for example, a positive test, a recovery from COVID infection, COVID death, are all inconsistent across regions and times. So it's very critical to define the semantics, the data schema and identifiers carefully with, the domain and IT experts in the loop. Now, apart from the representation, data entry process also typically are very primitive. Though we have a lot of apps, the usability is usually very low. And in the field, there's a heavy usage of multi-user editable Google Sheets, which neither scale nor have proper validation at the time of entry. So the data coming in typically tends to be pretty noisy. And the third aspect involves intelligent and scalable processing of all the data. And earlier I had, mentioned the data service layer, one of those green boxes, and all those aspects related to storage, privacy, security, compliance, they need to be solved. I'm not going to get into the details there, but this is something to be mindful of whenever you think of real systems. Now, in the data science layer itself, right, broadly speaking, there are 4 key areas of interest. The first one is intervention planning, and that's a mixed bag, and it involves deciding on the combination of lockdown policy, medical preparedness, and testing levels. And these 3 are interrelated because if we don't have medical capacity, then we need stricter restrictions. And making the right calls here requires being able to forecast how the economic and disease impact will pan out for various policy choices. And we also need to figure out the right control strategy, what is going to be the restriction policy. And the second area of analysis deals with optimizing the testing policy, whom to test, when to use what type of test, and also the allocation across different groups. And this requires understanding the test sensitivity, exploring test combinations and allocation algorithms so that we maximize the overall utility. And a third area of analysis deals with medical care policy and allocation. And again, this entails identifying the segments that are experiencing high severity and fatality levels and reallocation based on the modifiable risk. And a fourth area, which is now extremely important, is vaccination. So if you think about it, each vaccination is like a transaction that involves a vaccinator, vaccine materials, and a recipient, which needs to be scheduled at a physical place and time. And so this is very similar to the e-commerce domain, in fact. So there's a need to authenticate different actors, plan eligibility rollout based on the supply, and then optimize the sessions accordingly. As part of our engagements, we had to explore most of these problems to some extent. But in this talk, I want to give you a flavor of this work by taking a closer look at one of the problems we saw in the previous slide, which is epidemiological forecasting. Let me just stop here for a moment in case there are any questions. All right, let me go on. Yeah. So in epidemiological forecasting, the goal is to predict the case counts for various local regions, say districts or cities under different scenarios. So what you see on the right here are plots of 4 case count variables with time. And most of you would be familiar with these from the COVID trackers. So blue is confirmed cases, yellow is active, green recovered, and red deceased. And the COVID trackers show you the numbers so far till date. And our task is to predict the future counts. Now, it is important to qualify the forecasting scenarios of interest, like what are you expecting in future, right? And this could be this could correspond to a continuation of the status quo or specific changes in like the lockdown policies or testing or vaccination level. And there could also be assumptions on the inter-region flow. Say there is a lockdown and there's no inter-region flow, then the situation would be different from if there was like, free flow between different cities and so on. Now, there are multiple challenges to consider here. So first, we need to build models that are contextualized for different regions and time periods. And this is because the policies and conditions on the ground vary, as you can see from these plots, which are from 2 different cities of India. And again, what you see here are just 3 case counts, right? But in some cases, and that's often in fact, we might need to stratify these counts by age or severity, for example, oxygen beds, ICU beds, and so on. And so we require different models. And the accuracy or fidelity criteria also varies across application use cases. For instance, the considerations are different when you're trying to make a policy for lockdowns and if you're like trying to, plan for medical capacity which has a smaller horizon. And again, data quality issues are also something quite important to consider. So essentially, what we require is a robust data-driven parameter estimation, which is agnostic to model families and loss functions. Now, before we go to the solution, I also want to call out some key tenets which we need to consider. So obviously, it goes without saying that we want accurate and up-to-date predictions, but at the same time, it's also essential that the modeling mechanism is transparent and interpretable. And this is especially so because we know that the data that's being collected is not reliable. And we want health experts to verify if the dynamics matches with their expectations. And apart from that, it's also important to give decision makers an idea of the likely spread or the uncertainty of the forecast so that they can plan appropriately. And lastly, given the significance of the decisions being made, any modeling effort that we do should be set up to be reproducible and auditable by others. So keeping all of these tenets under consideration, so our team put together a consolidated forecasting process that essentially has 3 key phases. And the first one is the data operations. So this involved working with the government officials to consolidate, clean and consume data from a variety of sources, right? This was like hospitals, wards, mortuaries, a test portal and so on. And we had secure pipelines with semi-automated quality checks and monitoring. And this was required to handle manual entry errors, duplicates, spikes that you see, and like weekly periodicity because Sundays are holidays. And so here it was important for us to have a human in the loop because they had to track quality issues and changing data definitions. Like I called out earlier, what does a recovery mean? And you would be surprised to know the details, right? Because that definition has been changing over time. Now, the second stage was the core modeling phase. And here we developed a modular forecasting framework, which had data loaders, which could hook to a variety of data sources. And there was also support for multiple classes of models, multiple learning methods, loss functions, and the ability to log experiments for reproducibility. And the last stage is the report generation phase. And this had to be tailored to the needs of the end user. So in case of the government engagement, we had to incorporate information on upcoming policies like changing testing levels or festivals and so on to generate these forecasts. And we also adapted these forecasts to create like detailed custom reports like on staffing and equipment planning for the decision makers. So let me skip this and let's now take a deeper look at the modeling phase itself, like at the various classes of the epidemiological models. So as you know, there are tons of model families. So the question here is, how do we pick a good one? So usually this choice is driven by four main criteria, which are the columns in the slide that you see here. The first is expressivity, or the ability to faithfully capture the disease dynamics. And the second is learnability of parameters conditioned on the available data. And the third is interpretability, so that we can actually understand the evolution of the pandemic. And lastly, we have generalizability to future scenarios. So this is a little different from typical generalizability of machine learning models. We're talking about like generalizability with respect to new control inputs. Like say, if the scenario were to change, then can we adapt the model for that? Now, most of the existing models fall into three broad buckets. The first set is the curve fit models, where we try to fit the data to a curve with certain parametric forms, say exponential growth. And while these are easy to learn, the issue with these models is that they don't exactly capture the disease dynamics, and there's a big risk of going wrong in case of data quality issues. And the second group is compartmental models. And here the whole population is divided into different compartments based on the stages of the disease. And people move between compartments at some rates. So SIR and SER models are examples of this family. Now, despite simplistic assumptions on uniform mixing, most practical deployments tend to be based on these models because of their interpretable nature. But these still have to be designed carefully because we need to address issues of identifiability to make sure we can actually learn from the data. And the last group is agent-based models. So these capture behavior at the fine granularity of individual agents. And though these are very expressive, these models tend to have a lot of parameters, so that makes it difficult to calibrate with real data. And in our work, we experimented with all of these options, but the practical deployments were primarily based on the compartmental models. So let's have a peek at one such model. So consider the disease progression in the population. So in the beginning, we have a healthy but susceptible person. And after contact with a virus carrier, this person becomes infected. So he or she doesn't immediately start spreading the disease though. So there is an incubation period, which is a yellow block, typically 4 to 5 days before the person becomes infected, that is becomes infectious, that's the red block. Now at that point, the person begins to start infecting others. And after a while, he or she, either gets detected and is isolated or just stops being infectious. And that is the orange stage. And they could still test positive and require medical care, but they're not spreading the disease. And after a few days, the person would have recovered, and that is the green stage. And this is the happy path. There's also, of course, an alternate path that starts out the same way, but unfortunately, after detection, the person passes away instead of recovering. And then there is a third path, which again starts in a similar fashion, but the patient is not even detected because of lack of testing facilities or symptoms not being serious enough. Now, this path does matter because even though undetected, these infectious people are going around spreading the disease. In this case, we have no idea of the outcome, death or recovery. And what I showed you just now is a simple example, but there are a lot of variations of these compartmental models, which also accommodate vaccination and reinfections, which has become the norm now. Now, in a compartmental model, what we do is map these disease stages to compartments, and the population transitions are governed by ODEs, which are, these differential equations. So they look like this. I'm not going to get into the details. We're happy to discuss it offline. But the main thing to remember here is that there are a few important parameters. Like the first is the transmission rate. That is the number of people an infectious person infects in a day. Then there's the probability of detecting an infectious person, which depends on testing level, the probability of death versus recovery, and finally the average durations of all those different stages that I called out: incubation, infectious, and so on. And the big challenge is that these parameters vary across regions, time, and population groups. And there's also a dependence on the lockdown, testing, and vaccination policy. So we have no choice but to estimate these from actual observation using machine learning techniques. And in doing so, we encountered two important questions which required new research. The first was, how do we learn parameters from data in a model and loss agnostic way? And I want to re-emphasize that we are not tying ourselves to a specific model. I showed one model, which is an example of a whole family of models. Now, this is especially important because compartmental models are not very amenable to gradient-based learning. The second question was, how do we quantify uncertainty in this forecast? And to address the first problem, what we did was repurpose Bayesian optimization and sequential model-based optimization methods such as hyperop. So these are techniques people typically use for fine-tuning hyperparameters in deep neural models. And essentially, the idea is similar to the usual training paradigm. We quantify the model goodness in terms of an application-specific loss function, and we search over the feasible parameter space using Bayesian optimization. And the resulting optimal parameters are then used for forecasting the future. Now, for the second question on uncertainty, there are traditional methods based on MCMC sampling. We did try those out, but those are usually slow. So we came up with this novel Bayesian model averaging approach, which makes use of the different parameter sets which were already explored during the Bayesian optimization itself. And essentially, so essentially what we have is multiple models. So you can see all of these different blue curves here, which we get from the Bayesian optimization. And we induce a posterior on this model space, making some assumptions by looking at how well these models fit the data. Now, this gives a weighted ensemble of models, and we use this weighted ensemble to create a forecast distribution for any future date. Honestly, I kind of glossed over all the details here on how we initialize the models, how we handle identifiability, drift in distribution, convergence properties, and so on. But just want to emphasize that though I mentioned one specific compartmental model, what we really have is a big family of models which incorporate a variety of factors such as mobility, testing, vaccination, and so on. And these two core ideas, which is the using the Bayesian optimization and model averaging, right, apply to all of these. And let me now quickly show you some results from the city of Mumbai. So this is for the different stages of pandemic from last year. So the shaded region is used for training, which is, you can see the slightly gray area, and the unshaded one is the forecast. And the table shows the case count wise mean absolute percentage error loss. So for most of the stretch, we were able to maintain a single digit loss in spite of data reporting gaps and constant changes in policies and dynamics. And most importantly, right, while working with the government officials, we were able to uncover a lot of issues with the data collection pipeline itself, right? Like when things were being missed based on the analysis that we were doing with these models. So that was more useful to them, in fact, than the forecasts themselves. And we also, were contributing forecasts to the Rake Lab Forecast Hub, which is used by CDC in US. And I want to call out that the most important thing here is that what we finally generated for the war rooms was not just a forecast, but this was actionable outputs. So we used to give them 3 forecast scenarios corresponding to different quantiles, a planning scenario to provision for, a high scenario for contingency plans, and a low scenario as a reference. And for each of these cases, we gave them detailed requirements of staff and equipment, like how many oxygen beds do they need, how many specialists, doctors, ward boys, ventilators do they need for different care facilities. And that was something that they could readily consume. Yeah, I'm probably out of time, but just wanted to share some key learnings from this effort. So some of these pertain to the practice of data science, right? And the first thing that I want to call out is whenever you have drifting data and dynamic scenarios, you should have a human in the loop. And this is particularly true when you're predicting for the future. You need to incorporate all the information about the upcoming scenario from multiple sources. And that is why scenario condition forecasting goes beyond machine learning. And you need human experts to collate this scenario information. Think of these as control inputs in a control system. And the second thing I want to call out is paying attention to the data layer, because it's otherwise going to be a case of garbage in and garbage out, which was the case in a lot of our modeling exercise. And model interpretability and identifiability are also super important, because parameters are critical for understanding the dynamics on the ground and also the data collection gaps in real systems. And lastly, the application needs, right? The end user needs should dictate the formulation as well, and the modeling choices and the design of the final insights, because ultimately it's only when you customize the solutions and make the insights actionable, right, that they're going to adopt it, and that will lead to the maximal impact. Now, apart from this, right, I also had some valuable lessons which are like a little broader in nature while we were working on this effort, and something I thought was important to share. And the first was on achieving clarity on goals. So it was really, really important for us to work backwards from the end user pain points and question all the assumptions, right? So as data scientists, we tend to go and rush to solve, but first figure out the problem. And our focus had to be on the real human impact, because it's not always about the model accuracy. And the second lesson was about building collaborations with empathy. And this is critical in any large scale project, because the very nature of the work entails it. So even in my little corner, this picture was pretty complex. We had government officials, health experts, researchers, engineers from different orgs. And it was essential to develop an outside in, that is putting yourself in someone else's shoes perspective. And the last lesson was the importance of being nimble and adapting to changing circumstances. And this is especially true in a pandemic, where the situation on the ground, the problems of interest, data, definitions, everything evolved rapidly over time. And in our case, even the team changed as people rotated in and out, because it was a volunteer team. So it requires a special mix of equanimity and agility to take things in stride. And I would say in all of these things, it's not like we got these right, but these were important lessons. And whenever we got it right, it helped us do better. So just wanted to share, and some of the things that we are doing as a consortium, we are like putting together a playbook for future code-based publications and so on. So that's pretty much all I had to say. Thank you so much for the patience, and I'm happy to take questions. I don't know, I missed all the questions, so please, Dr. Halima, would love
Thank
to
you
hear about
so
those.
much. Thank you. It's extremely stimulating, especially in this time of COVID. But you know what? I took 3 times from Amani because she gave me the permission. So this is just for the audience. So thank you to I thank Amani for letting me know. So probably I will not take a question if you don't mind, but we will refer the question to you, since you told us that you can receive any question.
Oh,
privately.
definitely.
Appreciate that.
Happy to take any emails. Yeah.
I have plenty of questions, because I'm learning from you. I worked on SEER model last year, and it was very
Awesome.
interesting. Yeah, to manipulate all these parameter, given an interval. So thank you very much, Srujana, and it was a pleasure to meet you. And probably we'll have an opportunity to get in touch with you
Definitely.
and work together.
Definitely. Thank you so much for this opportunity as well. See you.
Thank you so
Bye-bye.
much. Bye-bye.